So, welcome to pattern analysis. The back is ending right now. And if we look at our schedule, so I had a small swap here. So last Thursday I talked about the dimensionality reduction, and today we will be talking about the variational inference. I kind of decided not to update the schedule because I thought maybe it's a bit clearer. And of course I will add the recording in here once we have it. And the reason why I was swapping things is that I was still working, let's say, or reworking the section on variational inference. It's probably arguably the most complicated topic that we have in the semester. And I wanted to change something on it in comparison to last year. Let's see how things play out. For the rest of the semester, we still have trees and forests, and then sequence models or graphical models, in particular hidden Markov models and Markov random fields. And there we will return to the normal, let's say, inverted classroom cycle then. Next Monday, so in 4 days or 5 days from now, I will be out of town, and there will be a demo session. We prepared a number of pieces of code for various algorithms that we have been discussing in the last few weeks. So my recommendation is to participate. I think it's going to be interesting. Today is Monday, so Thursday is a public holiday, and then Monday in a week from now, so that will be the demo session, so in 8 days. It will not be recorded, so you have to come in order to see it. And I think it should be interesting. So I will also send an email around to advertise this a bit more. Yeah. Okay. So variational inference, it's a bit of a complicated topic. It's in chapter 10 of the book, and I'm only going through the beginning, like until 10.2 or so, not look at the other variants of variational inference. But the way how it's presented in the book, and how I would also like to present this here, is to essentially generalize or expand this expectation maximization algorithm that we have been discussing into the variational inference framework. Okay, so very quick recap. Expectation maximization, that was for the Gaussian mixture model fitting. No? We had the expectation step, where we calculated the membership, like what cluster, what component created which sample, in terms of likelihoods, no? And then in the maximization step, the parameters were adjusted. No? If you want to refresh this, the video is also available, of course. So, in the expectation maximization algorithm, we said, okay, the expectation step is called expectation step because it calculates an expectation effectively of these hidden variables, Z. So what we require is that this expectation can be calculated, that it's tractable in some sense. What is this expectation? It's the expectation of the posterior, so of the hidden variables given the data and the parameters that we currently have, like the best estimate of the parameters so far, theta, times the complete data likelihood. So times the distribution that tries to make sense of the data and the hidden variables given our parameters, theta. Okay, so, and then in the maximization step, okay, we require a tractable maximization of the parameters theta, but this is usually the smaller problem. No? So the bigger problem is to make sure, is this expectation here in the expectation step tractable? Okay, so this is the starting point for the conversation. And now, when does this expectation become intractable? Well, it depends. So if this distribution of hidden variables grows, then it can quickly become out of hand, because we have to produce a distribution for all possible states. So it can just become intractable because of combinatorial multiplicity, or it can be intractable because we are not able to provide reasonable equations or so for it anymore. No? So these are, I think, the two main reasons for intractability. So in any case, if this posterior of the hidden variables becomes intractable, then we need another solution. And the variational inference framework is one way to do it. Another way would be the Markov chain Monte Carlo framework that we have already seen. For the Markov chain Monte Carlo, what we need are conditional distributions for each of these variables. In the case of the Gibbs sampling, a special case of the Monte Carlo framework. And then we iteratively sampled from these distributions to approach the target distribution. This is also something that will be included in the demo next week. Okay, and variational inference is another approach. So the idea here is to approximate this posterior of the hidden variables, and there are different possibilities how to approximate it. So you can say, well, I just use a set of functions that are easy to handle analytically, then it's not a problem at all. So we had this concept of these conjugate priors, you can use that and so on, and in order to compress things. But of course, this is a relatively restricted set of functions. There are so-called gradient-based approximations. We can make a bit more sense out of that in a second. And then we have factorization-based approximations with an approach that is called the mean field approach. And this will be the main topic of conversation later. But before we look into this, let's do a couple of other things. And here's the agenda. So first, I want to talk about variational calculus in general, just as a general background, just to clarify what it is. And it's not really complex, it's more like an illustration. Then we need to briefly talk about the Kullback-Leibler divergence, because it's a tool that we will be needing. And then we look at the generalized expectation maximization algorithm to understand the optimization that happens under the hood a bit better. And from that, we can look into the variational inference. So these are the 4 steps for today. Yeah, so I'm skipping proofs like almost everywhere. If you want to look at this, so in the book by Bishop, everything that we're talking about today is between sections 9.4, like the generalized EM, and then until section 10.2, variational inference for Gaussian mixture models. Okay, so let's go. Calculus of variations. So this is a math topic. Yeah? In the first place, has nothing to do with machine learning. Maybe you also are aware of it from a math class somewhere. So the idea is this. The goal is to study a so-called functional f that has this y here attached. And what is that? So this functional f acts as an operator that takes a function, well, sorry, this is supposed to be y, I'm changing this typo, takes a function y of x and returns the output value f. So y is the functional argument here that is changed. Yeah? So, and if we think about analogous fields, then what we know is standard calculus. In calculus, it's so we search for a value x that maximizes or minimizes a function f of x. So that's known from school. And the calculus of variations searches a function y of x that maximizes or minimizes this functional f of y. Yeah? Okay. And that's essentially, that's all. It has surprisingly many applications. So one example, the shortest connection between 2 points is a line. This can be shown with this calculus of variations. So in that case, the line would be, or what will be the line in the solution, would be a curve function. And then this functional is a method to calculate the length of the curve. And now we're trying to minimize the length, but in order to do that, we have to manipulate the curve. So we're changing the inner function in order to minimize or maximize like the overall expression. That's the idea. Yeah? Okay. Second example. No? A statement like entropy is maximal when the probability distribution is uniform. This is also something that has the very same problem structure. Yeah? So we have, we can say the probability distribution is, we can say is a function. No? We take that as a function. And in order to calculate the entropy on that function, we need to wrap it into this integral expression. Yeah? So that would be the f. So we want to maximize the entropy by somehow manipulating this probability distribution. And then we come to the result, oh, it gets maximal if we have a uniform distribution. Or if you look in the direction of physics, there's like a million cases where this applies, I think because they just nest their functions for some reason. So one rather arbitrary example is if you think about light paths through some medium or different types of mediums, then there is Snell's law that describes the refraction along the light path. Yeah, that would be just one example. Okay, so there are many applications of this, and just to give a little glimpse how it works without proving anything or so. Yeah, but again, coming from calculus, we can say if we don't have a closed form solution for calculating derivatives, I mean we do, but if we wouldn't have a closed form solution, then we could numerically approximate these derivatives by looking at a small change epsilon to that variable x. Yeah? And we would look at something like a a function evaluated at position x plus epsilon, and then somehow expand this. I mean, that's the stuff for the math class then, but y of x plus dy by dx times epsilon plus some error term that we're doing with this expansion in the order of epsilon squared. And then you would say, okay, if you take the limit that epsilon approaches 0, you get the derivative. And this also works for multiple variables, x1 to xd. Then you can take partial derivatives. So it smoothly extends to that. And for the functional derivative, one could do the similar thing. Could say, okay, I have my functional, and then I have an inner function, and I change it in a small direction epsilon, and do the very same expansion. Let's not go into the details there. So the variational calculus then is to vary this functional value. Yeah? And the rest is math literature, so let's not look further into this. There's also in the appendix of Bishop's book is a little bit of a derivation. I took these equations from there, but we will not further need them. Okay. So let's talk about a second concept that you might be familiar from some other machine learning class or so. And this is the Kullback-Leibler divergence. So in Kullback-Leibler divergence is something like a relative entropy, you could say. So let x be a discrete random variable with some states xi, and a probability that x assumes the value xi being p of I. Then the entropy h of p is the average information for the possible outcomes of x. So the entropy of p equals minus the sum over all possible outcomes of the probability of xi, okay, I could have just taken pi actually, times the log of pxi. And you could say, okay, in terms of applications, again, there are numerous applications. No? For example, in information theory, the entropy serves as a lower bound for encoding x. Okay, but let's say we don't have an optimal encoder, but instead we just have some encoder that someone gave to us. Then it's probably suboptimal, because how could that encoder possibly know the exact distribution of characters that we need to encode? So there's always a little bit of a mismatch, you could argue. So let's say the encoder is Q. So we don't have the optimal distribution, but we have only an encoder that encodes a distribution Q. And then one can look at the relative entropy, and this is the Kullback-Leibler divergence between P and Q, which is the entropy of P times the, what do we have here? We have the true distribution P of x, but the encoding of log Q. So, and we have the difference of that. So we can contract this and say this is the integral over all possible characters x, looking with a distribution that is the actual true distribution with which these symbols occur, P of x, times the log ratio of P of x divided by Q of x. So one can interpret this as the average additional required effort for encoding P. So we have an encoder, it contains all the symbols that we need, but it's just, if we think about an entropy encoding like a Huffman code or so, it's not optimal. So it has shorter code words for symbols that are more rare and vice versa. So what is the additional, the additional, let's say, number of bits or so that we are creating with this suboptimal encoder? Okay, it's just one way to think about the Kullback-Leibler divergence. You can also just say, okay, it's some form of like a distance measure or something. It's not a distance measure. I'm come to this, but something that gives you a difference between two distributions. Okay. So the Kullback-Leibler divergence is the expected log difference between distributions P and Q. So just to rewrite this once more, sometimes you have it like this, sometimes you have it the other way around. So you can write it as the sum or integral over the variable z, following the distribution P of z, log of Pz divided by Q. Or if you observe here the fraction with numerator and denominator swapped, here you still have the P, but then it would be minus that sum, would be the same expression. No? Okay. Yeah, so the interpretation is the expected number of extra bits for encoding text with distribution P with an optimal code for distribution Q. Properties that are important for the Kullback-Leibler divergence is that if I take the Kullback-Leibler divergence of identical distributions, so between P and P, then it would be 0. And for all other pairs of distributions, it would be larger than 0. No? So equality only holds if P equals Q. And the Kullback-Leibler divergence is not symmetric. So Kullback-Leibler divergence from P to Q is not Q to P. So, and this is why it's not a distance. Okay. So let's have a look at the non-negativity. So there is a tool, it's called Jensen's inequality. And Jensen's inequality says, if I have a convex function f, then graphically, if I look at it, things behave like this. There's a point A here on the left, and there's a point B here on the right. And if I follow the function between A and B, then I'm always lower than as if I would directly connect A and B. No? So in mathematical terms, if I follow the function f along some point between x1 and x2, so the t is like a linear interpolation of the coordinates. So I take a t portion, let's say 20% of x1 and 80% of x2, then I'm here on this line. Then I'm lower than if I would take the point, the function value of that point x1, the function value of that point x2, and linearly interpolate between this function value, which would be up here. That's all that Jensen's inequality says. And then you can say, okay, not a problem. It doesn't need to be a function in one variable, no? Or it doesn't need, it doesn't need to cover one point. But you can generalize this to many points, and it's the exact same expression. So the function of a sum of weighted points xi is lower or equal than a weighted sum of function values of fi. Okay. So if we apply this to the KL divergence, then it turns out that you can take this expression, so the sum over all z of p of z log of qz over pz, you can map this to this template that you say, okay, there's an outer function and I have a weighted sum of this. By saying p of z is my interpolator ti. And the function is the log. So the logarithm is concave. So the negative of the logarithm is convex. So Jensen's inequality is applicable. And that means that the log of the sum of pz qc over pz is lower or equal than the actual formulation of the Kullback-Leibler divergence. So the sum over all c pz times log of qc over pz. Don't worry about the minus. I took care of it. The minus in the KL divergence is cancelled with the additional minus for flipping log's concavity to convexity. So the left-hand side here is 0. You can cancel the p of c, and then only q of c is left over, and this has to sum up to 1, and the logarithm of 1 is 0. Okay. So the Kullback-Leibler divergence here on the right-hand side is larger or equal than 0. Okay. Yeah, and one can then also show that equality to 0 only holds if p equals q. This follows from the fact or the property that the log is a strictly concave function, but I skipped it. Okay. About the symmetry. Here's a plot or two plots about the values of the Kullback-Leibler divergence. On the left-hand side, it's the Kullback-Leibler divergence from P to Q. And on the right, it's the Kullback-Leibler divergence from Q to P. Here, totally unreadable, sorry for that. On the x-axis is the value P between 0 and 1. And on the y-axis is the value, or are values for Q from 0 to 1. And also here in the right plot, here is P and here is Q. And the whole thing here is a heat map. Brighter values, so more yellow values, are larger divergences. Yeah? Okay. So what do we see? I mean, the contrast is not so super great, but the non-symmetry is probably well visible. No? So if we imagine we take the Kullback-Leibler divergence as a quality metric to fit one model to an existing fixed distribution, what would happen? So if we look at the Kullback-Leibler divergence from P to Q on the left, then this has a large divergence if Q is small, where, small q means on the y-axis we are here in the bottom part. If P is large, so let's make P large, Now, if P is a fixed distribution and we want Q to be our model that we adapt to P, and we will get a lot of penalty if we are here in this region. So in areas where we have little probability for Q, if P is larger. So then we get penalty. So this means let me try. Hold on. Q will broadly cover low probability areas of P. Why is this? Hold on. Let's look at the second one and let's try to disambiguate this. The Kullback-Leibler from Q to P has a large divergence if Q is large, where P is small. Yeah. So this is I think this is the easier case. So here, if P is large, then Q also needs to be relatively large to avoid this penalty here on that part. So the Kullback-Leibler divergence between Q and P concentrates here on the high probability. The distribution Q concentrates here on the high probability areas of P. Whereas in the first case, it covers the low probability areas of P. I will make this argument a bit sharper and think about it again. But anyways, let's empirically look at what that means. So in our book, there are a couple of examples illustrating the impact of this. So if we look at the Kullback-Leibler as a fitting criterion of a Gaussian, if we look at the Kullback-Leibler divergence from Q to P and fit it here with an isotropic Gaussian, the red lines, to some Gaussian with a full covariance matrix, then the Kullback-Leibler from Q to P will focus on a mode in the distribution and will try to relatively narrowly embrace this mode. Whereas if as a fitting criterion the Kullback-Leibler divergence from P to Q is used, it tries to cover also the lower probability. I mean, it's not so that there's nothing out here, it's just that it's less likely, no? And the fit will then try to cover that area as broadly as possible. So this would be the alternative solution. Yeah? We can say, yeah, okay, so we will get a more compact estimate, apparently, if we use this Kullback-Leibler divergence from Q to P. But if we have a multimodal distribution, and this is the second example, then it has an even more, let's say, tangible effect. And this is the second picture here from the book, figure 10.3. So the order is swapped here, but here the true distribution is bimodal. So there are two modes in that distribution. And the parametric model that we have to fit it to that distribution is a single Gaussian, but with full covariance this time. Yeah? So if the Kullback-Leibler divergence from P to Q is used as a quality criterion, then again it tries to cover more or less the whole space. So a little bit of everything here. If we have the Kullback-Leibler divergence between Q and P, then it says, okay, I'm trying to focus on one of the modes here, and this might end up then on one mode or the other one. Which one? I don't know, no? But it's more, it depends certainly on initialization and whatnot, no? But so the individual solution, one could say, is better, no? but certainly it's a local optimum then in the space. No? Okay. Good. So back to our actual business. Let's talk about the generalized expectation maximization. So the generalized expectation maximization is a more abstract formulation of the expectation maximization algorithm. And I think that the purpose why we are talking about it is to disclose the underlying optimization a bit more clearly. So, so we distinguish three quantities. So there are observations x, there are hidden variables z, and there are parameters theta. What is the difference between an observation and a hidden variable? What is okay, that's also fair. But what is the difference between a hidden variable and a parameter? In the context of the GMM fitting, if we say, okay, we want to identify Gaussians that somehow constitute this distribution, then for every Gaussian we have a mean, can be a vector, and a covariance matrix, and this would be considered parameters. So in theta we just have mu1, sigma 1, just concatenated all these mu2, sigma 2, and whatever other components we have. The latent variables are what we learned in the expectation, when we talked about the expectation maximization algorithm, would be the responsibilities. Like if I have a couple of data points observed, then for every data point, I can wonder, like, was this data point created from this distribution? Because it's a generative model, so it should be able to produce data. No? Was it generated from this distribution, or was it generated from that distribution? Yeah? And this is the hidden variable, like what we don't know and don't see, or so you could say. No? So the hidden variables or latent variables. Hidden variables are the responsibilities, and these were little responsibilities. So these were distributions. So if we take this point here, just to give it a name, so that point, if we have two components here, would have two likelihoods here. No? One likelihood that I was created from component 1, and one that, I was created from component 2. And these are these responsibilities. No? So a value here for created from, and maybe these values, how do you get them, by the way? How can you calculate them? So I'm interested for this point. How can I calculate this? don't need to say the specific equation or so, but just the approach computationally. How can I get it? What do you think? Yeah.
Take that point and divide it by the total value of the specific area correlate to the theta and the
Sorry, you take the value. You take that, no? So you write something like, I'm not sure, I'm not 100% sure that I understood you right, but let me write something down and you can always intervene, yeah? So we can evaluate something like, okay, let's call this somehow P prime or so. Okay, so we can evaluate the probability that P prime has been generated by Gaussian number, I don't know, 1, for example, yeah? Covariance 1, right? And normalize, yeah, something like sum over all I, so over all components, and then I take, so P is really a stupid letter. Let me make this an X just for my sanity. Okay. Okay. So and then let's evaluate it for for all components that we have. No? Then we can and this to calculate is not so difficult. You can just plug it into this Gaussian equation. No? So you can say, okay, what I need to calculate is something like x minus mu. I divide this by sigma, or if these are vectors, then I take the covariance, something like this. It's probably a mistake here or there, but yep. And then we can e to the power of minus something, no? Can have our constant in front, or we leave it out because we normalize it anyways. And then, and that will be the specific value, yeah? So just to invent things, if we say, okay, if this is like 2 and some standard deviations away from component 2, and more than 3 standard deviations away from component 1, then certainly this will be, like down here, this will be a higher value, no? Something like, I don't know. Again, totally made up. But these are the hidden variables, okay. Whereas the parameters are these specific values that constitute the model, that we would also see if we would write down, like if you open a textbook, look, what is a Gaussian mixture model, no? Then you would see the parameters here. Oh, I forgot one parameter. What parameter is missing? So we have the means, we have the covariances, and we have the priors, yes. Zack, zack, okay. Okay, thank you. Right, so these are the parameters, these are the hidden variables. Okay. Yeah, so we can spell this out explicitly. In our textbook, it's explicitly spelled out. So then we can write, okay, a GMM model is the probability of making these observations given the actual mixture model described through its parameters is a model that actually also has these hidden variables involved. So these observations have been created from somewhere, and this is the Z that explains the somewhere from somewhere. So we have a joint distribution given these parameters, but we marginalized over all possible ways how this observation could possibly have been generated. So it could have been generated by this component 2. Yes, we see that, 70%. But it could also have been from that component 1. So we also have that 30% possibility here. Okay. And now if we think about, if we try to bring together what we know about the expectation maximization. Expectation maximization means in turns we update our belief about the responsibilities given the current parameters. Yeah? So whenever we update here our mean or whatever, we have to reevaluate the responsibilities. And then with these responsibilities, we have the maximization step that we say, okay, now we can calculate better parameters. And at the end of the day, we're looking for a description of these observations. This is what we're seeing here on the left-hand side. A description of the observations that is as good as possible, like through these parameters. So we're sort of it's again a maximum likelihood solution, yeah? Just with these hidden variables under the hood. If we bring this together with what we said about this variational calculus, no? That we said, yeah, in variational calculus, it's so we have an outer functional and then there's like an inner function that needs to be optimized. Yeah? And one could say, okay, the outer function is actually to properly fit these parameters and then to evaluate this P of x somehow. No? And the inner function is to figure out these responsibilities. So we can estimate the best possible parameters if we only find the correct assignment of these responsibilities. So this is the link, yeah, I would say, that brings us in the direction of the variational calculus. Okay. So the best variational responsibilities give the best possible parameters. Yeah. Okay. So in this picture, I brought it up in the EM lecture, no? Just to remind us, no? So the ground truth responsibilities, if you would use 3 Gaussians as a generative model, then you would know, okay, this component created this sample, that component created that sample, and you can keep track of it, no? And then just create a plot like colored like this, where every sample has the color from the component that created it. Yeah? And there can be a bit of an overlap. No? Okay. But then from an outside view, if you only see the observations, these colors are gone. And like all that you see are points. So now when you fit 3 Gaussians to it, then you're doing this inference about the responsibilities. And of course you get a result. This will not be the ground truth. I mean, how could it be, possibly? No? But it would be like your best belief or what you can tell from seeing this reduced form here of only the distribution of the points. No? And this is what is visualized here on the right. So, yeah, so during this expectation maximization iteration, these responsibilities, they are iteratively improved. And then eventually they contain these latent variables shall indicate the most plausible responsibilities, no? When we come out of this iteration, given the observations and the GMM parameters. So, and in order to formalize this a bit more, we can introduce a distribution Q of Z, and this shall be a distribution of latent variables. So here the shading, no? If there's a point somewhere between green and blue, it means that in that distribution of the latent variables, we are not sure. It could be component 2 or component 3, something like this. No? And in any case, this is an approximation to this true posterior distribution, and we can do more approximations there, as we will see very soon. Yeah, sorry. Yeah. Okay. So here's an important decomposition where this distribution Q will play a role. So the so-called log evidence, so this here our probability that we are making these observations given the parameters that we have estimated or will estimate. This expression can be decomposed into two factors. Yeah? So how does it work? It decomposes into a so-called evidence lower bound and into a KL divergence. So how does it work? First, we can rewrite this log evidence, can just plug in our joint complete data likelihood. So complete data means the observations and the hidden variables, and it's a likelihood because it's given the parameters, plus here our marginalization. And this will be decomposed into this elbow and the Kullback-Leibler divergence, which are two relatively scary-looking expressions, but we will get used to it. So what is the elbow, the evidence lower bound? So it's oftentimes written as this fancy L, a function of some helper distribution Q and the parameters theta, and it's a sum over all possible assignments, all possible values for the hidden variables of this evaluating the Q of these hidden variables, C, times the logarithm of the complete data likelihood, so the probability of X and Z, so observations and hidden variables given the parameters, divided by our distribution of the hidden variables, and the Kullback-Leibler divergence between Q and P. So this is that Kullback-Leibler divergence that focuses on one solution, yeah, is minus, again, we marginalize over all values for all hidden variables, Q of Z times the log of, here we have the posterior of the hidden variables, P of Z given X and theta, divided by our distribution Q of Z. Yeah? How does someone come up with this? Well, I'm not so sure, but if you want to follow up on this calculation, like why does it decompose like this? No? What you can do is that for the complete data likelihood here in the elbow, you plug in the identity of the logarithm of P of Z given X and theta plus the logarithm of p of x given theta. And then you have a sum here. You can split this. You can remove, you can cancel the Kullback-Leibler with this factor. And with the other factor, what remains eventually is, again, where we started, so our log p of x of theta. So it's fine. It's not like no harm done, yeah? But it looks a bit heavy. I give you that. So this evidence lower bound and the Kullback-Leibler divergence, they will play an important role now. Yeah? So we said that the Kullback-Leibler divergence is non-negative. And we're looking for a solution. So we're looking for parameters that maximize the probability of observing x given these parameters. Yeah? And now we know, okay, this probability that we want to maximize this with an optimal choice of the parameters theta, and we know that this expression is a sum of the elbow and the Kullback-Leibler divergence. And we know the Kullback-Leibler divergence is always positive. So that means that this L here, so p of x given theta is also always positive. So this means that the L here is a lower bound on, so is always lower than p of x given theta. Yeah? Okay. And this is why it is called evidence lower bound. So this is the evidence, and L is a lower bound on the evidence because there's always some additional non-negative factor that also may play a role. Okay, and our book visualizes it like this. I'm not sure that I like this picture, but I nevertheless took it here. So if p of x given theta is so and so large, we know, okay, there's the L that is so and so large, and there's a non-negative additional factor, the KL from Q to P, that is the rest. So, and the goal of this generalized expectation maximization is to iteratively improve our function Q of the hidden variables, and then the choice of parameters in the evidence lower bound. So the expectation step updates our belief about the hidden variables, the Q of Z, with the parameters that we had in the previous iteration. Let me call them theta old. And what happens there is effectively that the Kullback-Leibler divergence between our estimated responsibilities and the responsibilities as we can observe them with the current theta old becomes cancelled. So now we do the best possible estimate for Q. And then with this new Q, we can update the parameters theta. So we can maximize these parameters theta with our updated responsibilities, which brings us to a new location in the space. So this P of x given theta becomes larger, but again, this somehow creates a non-zero Kullback-Leibler divergence between our belief about the responsibilities and the best responsibilities that one could see. So this becomes larger than zero at that new location with these new parameters, theta nu. Okay, so so this is the, Now the maximization step updates the parameters, theta old to theta new. So So Q of Z that was updated will be plugged into the lower bound. So the lower bound with new parameters is essentially here an expectation using the responsibilities calculated still on the old parameters on a distribution that is governed by the new parameters. And we will do a maximum likelihood estimate on that to get these new parameters on the complete data likelihood, minus some expression that only depends on the old parameters. So this means if we are varying here these new parameters to get a new estimate, the second term here doesn't play any role because it doesn't contain any new parameters, so we can forget it a bit. So this update of the evidence lower bound for the new parameters is oftentimes written as an update of Q from the old parameters to the new parameters, plus some constant value that doesn't play any role for the update. So, and if you read something about the expectation maximization, oftentimes you see this Q function, the Q theta new, theta old, or Q t plus 1, t or so, to express this type of update here in the maximization step. Okay. Yeah, so to visualize this parameter update once more, so the new parameters theta new improve the lower bound and also the target likelihood P of x given theta new. And the gap between both quantities is then again filled with the KL divergence. So to visualize this, so we get, if we get to a new location, then the evidence P of x given theta is now improved, P of x theta new. The evidence lower bound is increased, and the gap between this new evidence lower bound and the actual evidence is then filled by the Kullback-Leibler divergence again, which will be filled with a recalculation of the hidden variables. Okay. So there's a picture in our book that I want to briefly, that I sort of dissected and that I want to briefly show. So let this be the target likelihood. The whole thing is some optimization, like some parameter space, and what target likelihoods of the evidence can we achieve here? Yeah? So this would be the optimum, no? But who knows how good our parameters are. So let's say these are our parameters. And with these parameters, theta old, this is the likelihood P of x given theta that we can achieve. Now, the evidence lower bound is can be seen as the blue function, and then the expectation step provides values for the hidden variables that close the gap to the current best evidence. So, and then and the M step then provides theta new, provides new parameters here at the top of this curve, and this will be the new Kullback-Leibler divergence. Okay. And then again, you could say, okay, now we iterate again, and iteratively, P of x becomes better and better with these two steps. Okay. Okay, so what is important for this? I think mostly important, is this decomposition in the evidence lower bound and the Kullback-Leibler divergence. So this is what we will effectively reuse. And this notion of iteratively adjusting the hidden variables. Yeah? And the iteration, okay, this visualization and so on is maybe nice, but it's not, but will not play a role in the future. Okay. So let's talk about the variational inference, finally. So the purpose of the variational inference is to model the posterior of the hidden variables given the observations with a distribution Q. So Q can, or is usually in variational inference, is an approximation to make the computation tractable. It's not the actual calculation. Yeah? So if the evaluation of the true P of probability of the hidden variables given observations and parameters, if you like, is infeasible, then you can say, okay, I define my distribution Q in such a way that it becomes feasible. And this is the approximation. No? But the rest of the calculation then runs through in an optimal way, you can say. And like what simplifications can one apply? I mentioned it earlier already. So we can, for example, use a parametric distribution, Q of z times omega, for example, where fitting the parameters omega is tractable. Or, and this will be the topic here, a factorized distribution where Q or where z decomposes into a number of isolated variables, C1 to Cm, and the joint distribution is then a product of these individual factors. Yeah? And it has to be factorized up to a point where you say, okay, now the remaining pieces, they are small enough such that I can do my calculations on them. Yeah? So this is what we will look at. We will briefly touch the Bayesian GMM model fitting, but not in too much detail. So, Bayesian model GMM fitting, if it's a fully Bayesian model, then it would mean that all model parameters are random variables, similarly to how we had it for the Markov chain Monte Carlo. So, what our book does is it totally abandons this theta and says, okay, like all parameters now become variables and they get their priors and so on, no? And he only continues to talk about Z. Like everything is a hidden variable now. So we only have observations and hidden variables. You know? Okay. There are also mixed forms, so you don't need to do it, but okay, I was following this path here. Yeah? Okay. So that means we define Q of Z as the variational distribution of all hidden variables. And we would like to apply now a technique that is called mean field approximation to solve this. It comes from physics, not by coincidence, but because in physics a lot of things can be solved with this variational calculus. So the idea is this: if Q of Z would be set identical to the true distribution of the hidden variables given observations, and sorry for not deleting the parameters here. If that is infeasible, then when one can make a factorization assumption that splits the hidden variables into M partitions. Yeah? So the distribution here, some variables are independent of others, and then they can be individual products. So we have little subdistributions Qi of little subgroups of variables set of I. And these are partitions in the sense that there's no overlap between these groups of variables. No? And they are independent, very much in the sense of independence earlier in the lecture, statistical independence. Okay, so the idea is that each factor Qi shall be simple enough to calculate an expectation, E of Qi, from it. And these expectations can then be iteratively optimized as previously seen in the expectation maximization framework. So let's just take again our decomposition. We have our evidence here, log evidence, log of P of x, decomposes into the log of the complete data distribution, P of x and z, and this decomposes into the evidence lower bound and the Kullback-Leibler divergence between Q and P. And then I kind of omitted it because it's a lot of math, but one can show that this evidence lower bound of Q can be rewritten for every individual factor. So evidence lower bound of Qj is the same as minus the Kullback-Leibler divergence of, so from Qj to some distribution tilde p, or p tilde, plus some other factors that will not change if we are optimizing Qj. Yeah, so plus constant. And what is this tilde p? So the distribution, so the log distribution of tilde p of x and zj, which supposedly is this, just expanded, is the expectation with respect to all these factors qi that are not qj, so all other variables. We could say the average, the weighted average of all variables that are not of interest, Zj, is formed on this joint distribution here. So this is just the integral over all these other variables. Times the log of the full distribution. Yeah? So effectively, it marginalizes out all factors that have no dependency to our Qj. So we take the true distribution Pj, where all irrelevant variables, from all irrelevant variables, we take the expectation and we try to match our variables Qj and our helper function Q to these variables in the true distribution after averaging out all the other variables. Yeah. So maximizing the evidence lower bound for the variables Qj is equivalent to minimizing the KL divergence. So we're trying to get Qj, so our approximation, equal to the true distribution where all other variables are averaged out. And so when this elbow, the evidence lower bound of Qj, is used to optimize Qj, then it's not disturbed by the other factors Qi, because we just take the weighted average and then can, along that axis, you can think about in the solution space, you look for a maximum, let's say, for the Qj. So how does this combine to a whole algorithm? It's literally just an iteration over these m independent sets of variables and minimizing their Kullback-Leibler divergence with respect to this distribution tilde p. So in turn, you visit all the independent variables. Okay, let's have at least a qualitative look here for the GMM fitting. By far, we will not go through all the details. The joint distribution for the Gaussian mixture model. Yeah? We have observations. I changed the set to a y because I found it confusing to have set here for all hidden variables and on the next page. So y are the responsibilities. Yeah? Then we have pi, the component weights. We have mu, the means, and we have lambda precision matrix instead of covariance matrix, but this is like one is the inverse of the other, so it's the same thing. Yeah? Okay, and from writing down this graphical model, what we can say is, well, okay, this decomposes already a little bit into the probability of making this observation given the responsibilities, the means, and the covariances or precision matrices times the responsibilities moderated by the prior probabilities that we would have an assignment here, then the prior probabilities themselves, here the means given the covariances or precisions, and the precisions themselves. Okay, so again, definitions as before, variables y, which component creates which sample, and so on and so on. Now, not every variable depends on every other variable, but still providing a full posterior for all variables is complicated. So the approach then here is to say, well, okay, not a problem. Let's capture all these variables in a variational distribution Q. So we have the variables y, pi, mu, and lambda here. And it suffices actually to only make these responsibilities independent of the other variables, pi, mu, and lambda, and then the whole expression becomes tractable. But actually it further factorizes if we recall the previous slide, so we still have the pi and mu and L as separate factors. So we have a total of 3 factors. This is Q1, this is Q2, and this is Q3. Okay. And then again, you do this Bayesian game, similar to the Markov chain Monte Carlo. So you need a conjugate prior for pi, which would be a Dirichlet distribution. Conjugate prior for the mean and covariances is a Gauss-Wishart distribution. And then you need to calculate the expectations for the factors y, pi, and mu lambda. And this goes on like until forever in the book. So I thought like, it's fine. If you're curious, like from page 476, it stretches for like 3.5 pages. Okay, and then, but then there are closed form expressions for the for the expectations. We can have a look at the PDF in a second. The optimization then consists of cycling through these factors and iteratively optimizing one variable at a time. So minimizing one of these Kullback-Leibler divergences at a time. And as a practical hint, the book states, let's start with a larger than necessary number of components, and in these iterations, you can remove clusters afterwards when the responsibilities there are very close to zero. And there's an example output here. Variational Bayesian mixture of k equals 6 Gaussians applied to the old faithful dataset, in which the ellipses denote the one standard deviation density contours for each of the components, and the density of red ink inside each ellipse corresponds to the mean value of the mixing coefficient for each component. The number in the top left of each diagram shows the number of iterations, and so on. Okay, so they start here with these 6 components, and after 60-ish, or actually after 120 iterations, essentially 2 components zoomed in on these 2 clusters, you could say here. The other 4 components are still there, kind of, but they have so little responsibility that in a post-processing step, effectively, they are removed. Yeah. So this is how this solution ends up with these two components. Let's have a look really quickly at Bishop's calculation, just to illustrate a little bit. I mean, I'm not expecting you to do this, but just to get an impression, like what does it mean to do these calculations? Yeah, okay, so here's the factorization. And now, in order to update this, one needs to iteratively calculate these expectations with respect to all variables that except the one that is actually optimized. No? Okay, so here we have the responsibilities. So we have an expectation here for these responsibilities. Here these are the usual equations for deriving the parameters of a Gaussian from the data. No? So the mean, the covariance, and the pi, the weight. Still goes on. I didn't look too much into the details, I have to admit, but anyways, more expectations here. But then what we end up is here an expectation for the mixture components, and this is an equation that is probably familiar if you recall what we saw in the Markov chain Monte Carlo variant of the dynamic Gaussian mixture model fitting. No? It was a very similar expression. It said, well, okay, the expectation for the component weight is a relative magnitude of the component relative to the total number of data points, how many data points are assigned to this component, plus some expansion factor, you could say alpha, that is like a hyperprior for the overall size of the solution. Okay. Okay, and then it's over, and there's the picture that I showed to you. No? Okay. So it still requires a lot of calculations, no? But I think it's a good technique to know, and I wanted to look with you also in this paper on the variational autoencoder, which combines a lot of these techniques that we have been studying now for a while now, a couple of weeks. Just to drive this point home, like these techniques, like even if you don't manually go through all the math, it's something that is actually useful, and it's still like used in systems in order to solve such optimization problems. Yeah? Okay, we will come to this. Okay, so now next Thursday we have a public holiday, and then on Monday we have that demo session, and then we will meet again. Okay, thank you. Questions? Anything? No? Okay, let's close the meeting.